The outer faces of a perfect natural crystal are not random. They result entirely from rigid internal mathematical constraints. In mineralogy, a crystal form designates a set of faces related to each other by symmetry, sharing an identical internal arrangement of atoms. A standard Miller index, like 111 enclosed in parentheses, maps a single plane. Enclosed in curly braces, it becomes a form symbol, a symmetry multiplier. Depending on the crystal symmetry class, that single coordinate replicates to produce up to 48 distinct faces. Understanding the form symbol allows us to predict the entire three-dimensional macroscopic geometry of a mineral from a single crystallographic coordinate. How these form symbols operate depends on the axis lengths within different crystal systems. A general form contains faces that intersect all of the crystallographic axes at entirely different lengths. Special forms occur when faces intersect two or more axes at equal lengths, or at exact multiples of a unit length. In lower symmetry systems, unequal axes mean a 111 plane hits varying distances, creating a general form. Higher symmetries shift these rules. Tetragonal systems require a 1-2-1 coordinate, while isometric systems with equal axes require intersections at distinct multiples, like 1, 2, and 3. The structural meaning of a coordinate changes based on the dimensional constraints of its host crystal system. Beyond axis intersections, crystal forms are categorized by their ability to completely enclose three-dimensional space. Open forms are sets of faces that extend infinitely in theoretical space. They do not enclose the central origin. The absolute simplest open form is the pedion, a single isolated face. Applying a central mirror plane generates a pinacoid. This open, two-faced form is made of strictly parallel planes, leaving the space between them unenclosed. Domes and sphenoids are also two-faced open forms. Driven by different intersecting mirror planes or twofold rotation axes, their faces intersect at the top while leaving the bottom entirely exposed. This creates a geometric limitation. A crystal composed entirely of petions or pinacoids cannot exist without intersecting supplementary forms. Because physical matter requires an enclosed volume to exist in 3 dimensions, open forms cannot stand alone. They must combine with other forms to seal. Open forms generated around a central line are called prisms. A prism consists of 3 or more parallel faces. The structure of a prism depends on the fold of its central rotation axis. A 3-fold axis creates a trigonal prism, while a 4-fold axis creates a tetragonal prism. Introducing mirror planes parallel to a 6-fold axis results in a 12-faced dihexagonal prism. Even with 12 faces, the top and bottom remain exposed. If those initial faces are angled toward the axis rather than remaining parallel, they become pyramids. They meet at a point, but the base remains open. Regardless of how many faces converge at an apex, a pyramid is geometrically classified as an open form. To create a finite crystal, crystallography relies on the mathematical interception of different open forms. Consider the tetragonal prism. As an infinite, 4-sided open tube, it requires capping. Adding a top and bottom pinacoid caps the tube. Where these flat horizontal planes intersect the vertical faces, the forms slice through one another to create a closed rectangular block. The macroscopic habit of a crystal typically arises from the Boolean intersection of multiple open forms, working together to enclose a finite volume. Closed forms are self-sufficient sets of faces that isolate a volume of space without the need for supplementary forms. When a mirror plane is positioned perpendicular to a rotation axis, an open pyramid reflects downward across it. This instantly seals the base into an 8-faced tetragonal dipyramid. Dipyramids are exclusively closed forms. Depending on their axial symmetry, they generate between 6 and 24 symmetrical faces. Other closed forms, like the 6-faced rhombohedron or the scalenohedron, are generated by 3-fold roto-inversion axes, which twist and offset faces on the top against identical faces on the bottom. Certain closed forms are restricted to specific systems. Dysphenoids possess only 4 faces and are limited to specific classes within the orthorhombic and tetragonal systems. Closed forms demonstrate how a single symmetry element, like a perpendicular mirror plane, can independently seal an infinite geometric structure into a finite object. The ultimate expression of symmetry in closed forms occurs in the isometric system. Isometric symmetry requires four intersecting threefold or fourfold axes, forcing the rapid replication of any coordinate entered into the system. The 1-1-1 octahedron is an 8-faced closed form constructed from 3 perpendicular fourfold axes and corresponding mirror planes. The 1-1-0 dodecahedron is a 12-faced closed form, resulting mathematically from truncating the edges of a theoretical cube. In isometric systems, the internal symmetry forces such immense geometric constraints that nearly all resulting forms are perfectly closed polyhedrons. Across the 32 possible combinations of mineral symmetry, these operations generate exactly 48 unique mathematical forms. These forms are strictly divided. 18 remain open, requiring combination, while 30 are closed and independent. When observing a natural crystal, we can mathematically untangle its overlapping sets of general and special forms. A complex crystal can be deconstructed into its constituent parts, such as a ditetragonal pyramid resting on a ditetragonal prism. The exterior shape of the crystal precisely maps the underlying symmetry of the core axes and mirror planes. Every face on a crystal is a strict vectorial property dictated entirely by these internal atomic constraints. Whether analyzing a single pedyon or a 24-faced dihexagonal dipyramid, the geometric logic remains constant. By decoding the form symbol and mapping the rules of open versus closed structures, we can reverse engineer any mineral's physical habit back to its foundational mathematical axioms.